Hey guys, welcome back to part 2 of the 5 M's of our Earth and Space Science course for our first pre-unit before we actually get into the geology of the Earth. So today we are going to be looking at maps and models. So moving into maps, long ago people had to rely on maps made by travelers and explorers, and a lot of times they weren't very good. They tried to make their best representations that they could, but either way, whenever you're traveling long distances and exploring new countries and continents, you want to be able to have the most accurate map on hand. But now we don't need that, right? We have satellites to make this job much, much easier. However, people still make maps today, and this is known as cartography. The accurate data that you can actually get from a map is necessary when helping to describe locations. So cartographers use a global grid to help determine these precise locations. Latitude and longitude. Latitude is the distance north or south of the equator, measured in degrees. We're going to talk a little bit more about both of these in just a moment. But latitude, these are the lines that are running east and west. Then we have longitude. Longitude is the distance east or west of the prime meridian, and it is also measured in degrees. And these are the lines that run north and south. Combined, as you can see on the map here, these form a grid. So digging into lines of latitude a little bit more, these again are the lines that are running east and west, and they complete circles around the globe. All points on that circle have the same latitude. 1 degree of latitude is equal to about 111 kilometers on Earth's surface. So from the equator, which is at 0, or if we look at this picture, 0 degrees is the line of latitude for the equator, and 90 degrees is the point at which the North Pole is. So every single degrees, 1 through 90, that is going to be, on average, about 111 kilometers on Earth's surface. The line of latitude around the middle, again at 0 degrees, is known as the equator, and the equator divides the Earth's into two halves. And these are known as hemispheres. So we have the northern hemisphere, which is everything north of the equator, and of course the southern hemisphere, which is everything south of the equator. When we look at lines of longitude run north and south. The prime meridian marks 0 degrees of longitude. As we can see on the map, the line that is signified by 0 degrees actually runs through a city in England known as Greenwich. Since the Earth is 360 degrees in circumference, as any sphere is, from the prime meridian at 0 degrees to the 180 degree meridian, divide the Earth into eastern and western hemispheres. So anything that is west of that prime meridian is going to be the western hemisphere. And same for the eastern hemisphere, anything east of that 0 degree prime meridian line. So a degree of longitude varies in size. It's about 111 kilometers wide at the equator. And as you can tell by the picture on the right, as you get closer towards the poles, those lines get closer and closer together. It's only at the equator, at its widest point, where every 1 degree of longitude is going to be about 111 kilometers wide. It will eventually decrease to 0 kilometers wide at the North Pole and the South Pole. Furthermore, with longitude and latitude, the degrees of longitude and latitude are further divided into smaller units, and we call these minutes and seconds. So there are about 60 minutes per degree and 60 seconds per minute. An example, Cranberry High School, is located at these coordinates: 41 degrees, 22 minutes, and 1 second north, and 79 degrees, 42 minutes, and 46 seconds west of the prime meridian. To further our discussion, models are what science uses to help with understanding of certain things. They provide a visual representation of something. So for example, here we have a model of the Earth, and it's often depicted as what's known as a globe. All right, this actually shows a more realistic version of the shape of the Earth's surface. A model of a molecule can often help individuals understand the complexity of the bonds and structure between atoms. So having a visual representation helps us to grasp a better understanding of that specific thing. So when we take a look at a globe, we notice that it's obviously spherical in shape, but there's a problem with that. And the problem is that it's hard to put a globe into a book or onto a wall like a poster. So typically we need to transfer that image, that round spherical image, as a flat representation. And a lot of cartographers have had a lot of issues with taking a spherical image and turning it into a flat image. So with all of that said, can all of Earth's features be accurately represented on a flat surface without distorting them? And the answer is no. All right, so no matter what kind of map is made, some portion of the surface will always be too big, too small, too distorted, or just out of place. Cartographers have found ways to limit the distortion of each of these, the shape, the size, the distance, and the direction. But generally, when you try and fix one, it's going to exaggerate another. And we're going to take a look at some examples. So our first example is known as the Mercator projection. And on this map, you see lines of longitude, right? And those lines are parallel. And this makes the grid actually rectangular. Unlike when you look at a globe, all of those lines of longitude near the poles are coming together at a point. Now this depiction actually helps show directions more accurately, and it actually distorts the sizes and distances the farther you get away from the equator. So it happens to be a very inaccurate representation of the Earth. Next we have the Robinson projection. Robinson projection was an attempt to minimize the overall distortion while showing the entire world. Now, this map shows most distances, sizes, and shapes somewhat accurately. However, most distortions occur again near the edges. Next we have the conic projection, and these are actually made by wrapping a cone of paper around a globe at a specific line of latitude, and the lines are projected down onto the paper. The distortions increase the farther you get away from the starting line of latitude. So in this example, you can see that the paper actually comes in close contact with about the central United States. So right across the center of this map is going to be the most accurate. But the farther you get away from that central area, the more distorted things begin to be. Our next example is known as the mnemonic projection. And the lines here are actually projected from a single point onto the globe. So it's as if you were to have a bird's eye view of a specific area. The distances and directions are distorted on these maps. Once again, the farther away you get from that point of contact. This map is useful for showing the shortest distance between any 2 points. Then we have topographical maps. Topographic maps focuses on the surface features of an area. These maps can actually show a three-dimensional surface in 2 dimensions. And they do this by showing us the elevation using what are known as contour lines. And as you look at this map here, you can generally see that you have specific shapes that start to come out. Some spots look higher than others, and you can actually pick out what areas are the lowest in that region. Expanding on the idea of topographical maps here, let's talk about contour lines a little bit more. So a contour line is actually used to indicate the elevation of land, which is the height above sea level. Every position along a single line, or a single contour line, has the same elevation. So, as an example, if you're looking at this map, this circle here, along that line is all of the same elevation. Same for this one right here. If we follow this line the entire way around, it's all going to point out the same elevation along that line. An adjacent contour line represents a change in elevation. So the next line over beside it is going to be either a drop in elevation or an increase in elevation. There's also something known as the contour interval, and this tells you the difference in elevation between lines. So often every 5th line is bolded and labeled, and this is called the index contour. So every bolded line that you have here on this example, they don't have this one labeled, but it helps us visualize every 5th line. Now when you're looking at these lines a little bit closer, you'll notice that some lines are closer than others. And this actually indicates that there is a steep slope. It's either a fast rise in elevation or a fast drop in elevation. Lines that are farther apart indicate a gentler slope. So contour lines actually never touch except where there is going to be a vertical cliff. Another aspect of contour lines are known as hasher lines or tick marks. Hasher lines actually indicate a depression or a drop in elevation. If you look at the example down here in the bottom left, we have a contour line with these little hasher lines or tick marks, and those indicate that there is a drop in elevation that are pointing in the direction of those lines. So if we start at this line, we're actually, as we move towards the center, we're actually dropping in elevation. Same for up here. If we look at this example, we have a large hill with a rounded top, and then a second hill that is shaped a little bit more like a volcano, so it has a crater at the top, right? And the way that they're actually created is we know that there is a contour line and its adjacent contour line. We have an increase in elevation by 10. So say we'll go 10 meters, 20 meters, right? It says 20 here. 30 meters, 40 meters, 50 meters, and then the top of it, it doesn't reach 60 meters, so it could go up to 59.9 meters. But we know that it either levels off or it's kind of rounded off up there, so you can see that up here. Then it'll drop back down, 50, 40, 30, so it will stay in between 20 and 30 as we move across here. Back to our elevation of 30, 40, 50, and then we have a drop in elevation because we have those hasher lines indicating that. So it actually drops beneath 50, but not quite to 40, or they would have that marked. Okay, back up the other wall to 50, then back down 40, 30, 20, 10. So from this example, as you can see, at one point where we draw a line across, we can actually figure out what the topography of that area looks like. One last thing about contour lines is that they actually show the direction of which way water can flow. So rivers are always shown on a topographic map as a line running perpendicular to the contour line. So as we see here, we have this very dark, thick black line, and we know that since it's running perpendicular to these contour lines, that it must be a river. Now these lines bend. If we look at the contour lines, right, they actually bend or V, and they point upstream. So as they curve along the river, they point to where it's coming from. All right, so here's an example, right? It kind of V's, so it's pointing in the direction where the water is coming from. So we know as we run up through the V's, it's going to take us towards the mouth of the river. Our last type of map is known as a geologic map. And this is something that we might end up taking a look at here a little bit later. So in addition to topography, it is often needed to know the type and the age of rocks that are exposed at the surface. So once rock formations are identified, they then map them, and then each formation is assigned a specific color or pattern based on the age of that rock. But that's all we have today on maps and models. So if you go ahead and click on part 3, we'll finish up this pre-unit. I'll see you there.